So in this lecture, I will consider normed linear space. So a definition, we consider a linear space which will be represented by X. It has a field, K, which will be either R or C. And we say that a norm, so a norm which I will represent by n, it's a function from x to r plus, which enjoys three properties. The first one is that n of x, it's always non-negative, as I said, and n of x, it's equal to 0 if and only if x is equal to 0. The second property is that, well, and this of course holds for, I'm requiring that for all x in x. Now for all alpha in k and for all x in x, we want that the norm of alpha times x to be equal to the absolute value of alpha times n of x. And finally, a triangular inequality. So for all x and y in x, we require that nx plus y to be less or equal than nx plus ny. So a function from x to r plus, is called a norm if it satisfies these three properties. And from now on, I will represent nx by this symbol, double bar x. So two observations before we proceed. The first one is that if you take 2 points x and y and 2 elements of x, what I claim is that the difference between the norm of x and the norm of y, these are real numbers. I'm saying that the absolute value of this difference, it's bounded by x minus y. And so let me prove this inequality. So first, let me write that x, it's equal to x minus y plus y. And by the triangle inequality, this is bounded by x minus y plus y. And therefore, x minus y, it's bounded by x minus y, the norm of x minus 1. And by exchanging x and y, we get that y minus x, it's bounded by y minus x. I will prove in a second that this is equal to x minus y. And therefore, we have that both x minus 1 and y minus x are bounded by x minus y, from which this inequality follows, provided I prove this identity. And this is my second observation. I should have started with this observation, is that, well, the norm of minus x, it's equal to the norm of x. And this is very simple, because the norm of minus x we have seen is equal to minus 1. So the scalar product of minus 1 with x. By the property of the norm, this is the absolute value of minus 1 times the norm of x. And the absolute value of minus 1, it's 1. So this is equal to x. So we just proved that the norm of minus x, it's equal to x. So this is what we are using in this inequality. And therefore, we prove these two facts. Norm of minus x, it's equal to the norm of x. And also, the absolute value of the difference of the norms, it's bounded by the norm of the difference. Now, once we have a norm, we can define a distance. So I'll define dxy. So d is a function from x times x to r plus. And it's defined as, and I will call that the distance between x and y will be given by y minus x. And what I claim is that with this definition, all the properties of a distance are satisfied. So remember, of such a function is a distance if distance between x and y, I'm sorry, it's always non-negative, and that the distance from x to y equal to 0 implies that y is equal to x. But this is certainly satisfied because, well, the distance between x and y is a norm, and we have seen that the norm is always non-negative. On the other hand, if the distance between x and y is 0, this means that y minus the norm of y minus x is equal to 0, and we have seen that this implies if the norm of y minus x is equal to 0, this implies that y minus x is equal to 0, which means that y is equal to x. So the first property of the distance is satisfied. The second property, which is symmetry, is that the distance between x and y is equal to the distance between y and x. This is also satisfied because the distance between x and y by definition is the norm of y minus x, and we have seen that this is equal to the norm of x minus y, which is the distance between x, y, and x. And finally, the third property, which is the triangle inequality, we require that the distance between x and z to be less or equal than the distance between x and y plus the distance between y and z. Well, but the distance between x and z, it's z minus x, the norm of z minus x. I can rewrite the norm of z minus x as the norm of z minus y plus y minus x. Now use the triangle inequality for the norms. So this is less or equal than the norm of z minus y plus the norm of y minus x. Norm of z minus y, it's the distance. So let me continue here. This is the distance between y and z. And the norm of y minus x is the distance between x and y. And this is exactly the inequality we were looking for. The distance between x and z, it's bounded by the distance between x and y plus the distance between y and z. So once we have a norm in our linear space, this defines a distance. And once you have a distance, you have a topology, which means that you can define converging sequences, saying that xn, the sequence in x, will converge to a point x if and only if the norm of xn minus x converges to 0. And once you define this convergence, you can define open sets, closed sets, compact sets, and these concepts will play a very important role in the theory of normed linear spaces. So this is to mention the distance. So now we can talk about metrics which are equivalent. This means that if you have in a linear space X two different norms, say norm 1 and the norm 2, we will say that these two norms are equivalent So these norms are equivalent if there exists a constant which is strictly positive and finite, such that for all x in x, you have the constant c times the norm of x, 1. It's bounded by the norm x with respect to second norm, which is bounded by 1 over c times the norm of x with respect to the first norm. And, well, you see that equivalent norms will give rise to the same topology if you have a sequence xn converging into x in the norm 1. It will converge to x in the norm 2 due to this inequality. And if you have a sequence xn converging to x in the second norm, it will converge in the first norm due to the first inequality. So equivalent norms give rise to the same topology, therefore to the same open and closed sets. So now let me mention some normed linear space. So we are given a linear space X with a certain norm. What I claim is that if you have Y subspace of X, then Y with the norm defined on X, it's a new normed linear space. And this is clear, right? So if you have Y a subspace, a linear subspace of X, of a normed linear space, then you just use the norm defined on X in Y to obtain a new normed linear space. So this is clear. A second example is the product space. So assume that you have a space X1 equipped with a norm 1 and a second space X2 equipped with a norm 2. Now I want to define a new space which is X1 times X2. This is the space of all pairs X1, X2 in which X1 belongs to X1 and X2 belongs to X2. This is clearly a linear space. You define the sum, the addition of two elements by adding coordinate y's, and you define the multiplication by a scalar just by multiplying each coordinate. So here I'm assuming that both X1 and X2 have the same field as the space of scalars. And now, well, I can define a norm in the space X1 times X2. Well, actually, we can define it in many ways. So here are 3 possible ways with which I can define a norm on this space. One possibility will be just to define the norm of the point X1, X2 as the sum of the norms. So I leave to you to check that with this definition, this is indeed a norm, which means that with this definition, all the 3 properties of a norm are satisfied. A second way in which we could have defined is just, here's a 1 missing. It's just taking the maximum. The maximum between those 2 values. what I claim is that if you define the norm of the pair x1, x2 through this maximum, you get a norm. So again, you have to check that with this definition, all three properties of a norm are satisfied. A third way in which we could define the norm and would be to take the square root of the square of the first norm plus the square of the second norm. And again, I leave to you to check that with this definition, the norm, what we define, it's indeed a norm, satisfies the three properties. And moreover, as an exercise, I leave it to you to check that all these three norms are equivalent in the sense I just introduced. A third example is the following. Assume that Y, it's a linear subspace. Let me define Y bar as the closure of Y. So the closure, remember, is the set of all points x in X such that there exists a sequence xn in Y such that xn converge to X. So Y bar is the subset of X formed by all elements of X which can be approximated by elements of Y. What I claim is that Y, it's a linear subspace. And this is very easy to check. I leave that to you. And therefore, that if we equip the closure of Y with the norm, we have a new normed linear space formed by the closure of Y together with this norm. Now, a more interesting example is the following. Assume that Y, it's a linear subspace of X which is closed. So I'm assuming that Y, it's closed. So in a previous lecture, we defined the space, the quotient space of X modulo Y, which is represented by this symbol, and which is formed by all equivalence sequences. And remember, the equivalence sequence X is the set of points Z in X such that Z minus X belongs to Y. Okay. So we have seen that this space is a linear space, and we have seen how to define addition and multiplication by scalars. Now I'm assuming that in this space X I have a norm, and what I want to do is to define a norm in this space. So I want to define the norm of this equivalent class. And what I propose as a definition for this norm, it's, well, this is a subset of X. It's to take the infimum over all norms of Z for which Z belongs to X. And what I claim is that this is a norm, and we will check so that this is a norm in the space X modulo Y. So we will check the three properties of a norm. Well, first, remember that the zero element of the space X modulo Y, so the zero element is the set of all points for which z minus 0, which means z belongs to y, so this is exactly equal to y. Okay? I will need this observation in the proof that this is indeed a norm. So let's now check the three properties. The first one is that this norm is non-negative, and that if it's 0, then the element is 0. So let's check this property. First, that it's non-negative, it's clear from the definition, because we are taking an infimum over non-negative numbers, and therefore we get a non-negative number. Now let's assume that we have a point x in our quotient space, and assume that its norm it's equal to 0, and we want to prove that, well, this element is actually the neutral element of the quotient space, which is y, the set y. Well, if x is equal to 0, this means, by definition, that this infimum is equal to 0. So the infimum over all norms of z, such that z belongs to x, that this is 0. But z belongs to x, this is all z, such that z minus x belongs to y. And, well, if this infimum is 0, this means that we can find a sequence zj in my equivalent class x, such that the norm of zj it's converging to 0. Now, zj minus x, it's an element of y. So the norm of zj converging to 0 means that zj is converging to 0. Now, zj minus x belongs to y. Since zj is converging to 0, this means that zj minus x is converging to minus x. Since y is closed, and here I'm using the assumption that y is closed. Since y is closed and every point belongs to y, the limit belongs to y, this means that minus x belongs to y. And since y is a linear space, this means that x belongs to y. So we just proved that if the equivalence class of x has norm equal to 0, this means that x belongs to y. And what I claim is that if x belongs to y, and this is what I'm proving here, if x belongs to y, then the equivalence class of x coincide with the equivalence class of 0. So let's prove this implication. To prove that these two sets are equal, we have to show that one is contained in the other and the other is contained in the one. So let's take a point z in the equivalence class of x. Well, but this means that z minus x belongs to y. But since x belongs to y and y is a linear space, z minus x plus x also belongs to y, because y is a linear space and x belongs to y, and this is z. So this means that z belongs to y, and if z belongs to y, z belongs to the equivalence class of 0, because, well, by definition, the equivalence class of zeros are all points z such that z belongs to y. So this proves that the equivalence class of x is contained in the equivalence class of 0. So now let's prove the reverse condition. So I want to prove that the equivalence class of 0 is contained in the equivalence class of Z. So let's take an element Z in the equivalence class of 0. So by definition, this means that Z belongs to Y. But now, since X belongs to Y and Y is a linear space, this means that Z minus X belongs to Y. And Z minus X belongs to Y means that Z belongs to the equivalence class of X, which proves this implication. So if I have X an element of Y, then the equivalence class of X is actually equal to the equivalence class of 0. And therefore, we proved the first claim. So we've seen that if the norm of an equivalence class of X is equal to 0, then X belongs to Y, which means that actually the equivalence of class of X is the neutral element of the quotient space. So this is the first property of a norm. So now let's prove the second property of a norm, which is that let's take alpha a scalar, and we want to show that alpha times an equivalence class, the norm of that, it's equal to alpha times the norm of the equivalence class. Well, but this is easy. So by definition, the norm of alpha x, well, what is the element of alpha x? We have seen that this is the way in which a scalar multiplies an equivalent class. It's by taking the equivalent class of the scalar times the element x. And now, by definition, this is the infimum of all z, the norms of z, such that z belongs to alpha x. So this is by definition of the norm. Now, this set, it's the z's, the norm of z, such that z belongs to alpha times the equivalent class of x. Now let's assume for the moment that alpha is different from 0. We'll prove this identity in a moment in the case in which alpha is equal to 0. So if alpha is different from 0, saying that z belongs to this set is the same thing as saying that z divided by alpha belongs to this set. So this infimum, it's equal to the infimum of the norms of z, such that z divided by alpha belongs to x. Well, but now I can divide it z by alpha and multiply it by alpha. But when I multiply an element, the norm of this new element, by the property of the norm, it's equal to the absolute value of the scalar times the norm. This is by definition of the norm on the space X. So I can remove from the infimum the absolute value of alpha, and I get that this is the infimum over z divided by alpha, such that z divided by alpha belongs to the equivalence class of x. And, well, I can replace z divided by alpha by y, and this infimum becomes the absolute value of alpha times the infimum of the norm of y for y in x. Well, but this is exactly the definition of the norm of the equivalent class of x. and therefore this proves that indeed the norm of alpha times the equivalent class of x, it's equal to alpha, the absolute value of alpha, times the norm of the equivalence class of x, in the case in which alpha is different from 0. So let's consider the case in which, so we proved that identity in the case in which alpha is different from 0. So now let's consider the case in which alpha is equal to 0. But if alpha is equal to 0, the right-hand side is just 0, because, well, the absolute value of 0 is 0, while on the left-hand side, what we know is that this is the norm of, well, alpha x, the equivalent class of alpha x. Alpha is 0, so alpha times x, it's, we have seen it's 0, so this is the norm of the equivalence class of 0, which is 0. So indeed, we have that the right-hand side is equal to the left-hand side because both are equal to 0. So we have proved this identity in the case in which alpha is equal to 0 because both sides are 0. Let's now prove the third property, which is the triangle inequality. So we want to show that the norm of the equivalence class of x plus y is less or equal than the norm of the equivalence class of x plus the norm of the equivalence class of y. So let's use the definition first. So let's consider the left-hand side. We know that the sum of these two equivalence classes is given by the equivalence class of the sum. So this is how we define sum in the quotient space. Now, by definition, the norm of the equivalence class of x plus y is given by that infimum. So this is the infimum over all norms of z, such that z belongs to the equivalence class of x plus y, which is the equivalence class of s plus the equivalence class of y. Right? I did two steps here. I first have that z belongs to the equivalent class of x plus y, but the equivalence class of x plus y, it's the equivalence class of x plus the equivalence class of y, and this is what I wrote. Now, we have seen also that if we have two sets, the sum of these two sets, it's formed by all elements, which can be written as the sum of one element in x in this set and one element in this set. So this means that this infimum is actually equal to the infimum over all z, in which z it's equal to z1 plus z2, z1 in the equivalence class of x, and z2 in the equivalence class of y. So let me write z here as the norm of z1 plus z2, because, well, z is equal to z1 plus z2, and therefore this infimum is actually an infimum over the norms of z1 plus z2, where z1 belongs to the equivalent class of x, z2 belongs to the equivalence class of y. And now, by the third property of norms, I know that the norm of z1 plus z2 is less or equal than the norm of z1 plus the norm of z2. So this infimum is bounded. It's less than or equal to the infimum over the norm of z1 plus the norm of Z2, where Z1 belongs to the equivalence class of X and Z2 belongs to the equivalence class of Y. And what I claim is that this is bounded by the infimum of Z1, the norm of Z1, where Z1 belongs to X, to the equivalent class of X, plus the infimum of over Z, the norm of Z2, where Z2 belongs to the equivalent class of Y. I have to prove that. I'm claiming that this holds, but if I prove that, you see that on the right-hand side, I have exactly the norm of the equivalence class of X plus the norm of the equivalence class of Y, which is what's written here. So if I'm able to prove that inequality, I would have that the norm of the equivalence class of X plus the equivalence class of Y, it's less than or equal to the norm of the equivalence class of X plus the norm of the equivalence class of Y. So to complete the proof, what remains to be done is to show that this inequality holds. So let's prove that. This is very easy. So if either of these infimum are equal to plus infinity, there is nothing to prove because the right-hand side will be plus infinity, and that certainly will be larger or equal than an expression. So I can assume that both infima are finite. If both infima are finite, I fix an epsilon, positive. Then I can find, let's say, a W1 in the equivalence class of X such that, well, the norm of W1 almost attains this infimum. This means that the infimum, which appears over there, which is the infimum of Z1, such that Z1 it's in X, in the equivalence class of X. So this is certainly less or equal than the norm of W1, but I can choose one which almost attains this infimum, so this will be less or equal than the infima of Z1, such that Z1 is in X, in the equivalence class of X, plus epsilon. And in the same way, I can find a W2 in the equivalence class of Y, for which the norm of W2 almost attains the infima. So I have these W1 and W2 satisfying the inequality on the right-hand side. Of course, it also satisfies the inequality on the left-hand side, but I won't need that. And from that, I obtain that this infima of Z1 plus Z2 such that Z1 it's in the equivalence class of X and Z2 is in the equivalence class of Y. This infima is certainly less or equal than the norm of W1 plus the norm of W2. Right? Because W1 it's an element of the equivalence class of X, W2 an element of the equivalence class of Y, and therefore this infimum it's less than or equal than the norm of W1 plus the norm of W2. But the norm of W1 it's bounded by this infimum plus epsilon, the norm of W2 is bounded by the second infimum plus epsilon. So what we have is that this expression is less than or equal than the right-hand side plus 2 epsilon. This holds for all epsilon, so I can take epsilon to 0 to get that indeed the left-hand side is less than or equal to the right-hand side. And this completes the proof of the third property of the norm defined by this expression. So now we can define what is a Banach space. So let me just remind you what is a Cauchy sequence. So we have a sequence xk, k larger than 1, xk in x. This is called a Cauchy sequence. If for any epsilon strictly positive, I can find k naught such that for all j and k larger than k naught, the norm of xj minus xk it's less than or equal to epsilon. So this is the definition of a Cauchy sequence. Now, let me remind you what a complete space is. So I'll say that x is complete if every Cauchy sequence converge. This means that if you take xk to be a Cauchy sequence, if x is complete, this means that there exists a point x in the space x such that xk converge to x. Right? So x is complete if whatever Cauchy sequence you consider, you can find a point in x with the property that the sequence, the Cauchy sequence xk converge to x. And so finally, a Banach space, so a Banach space is a normed linear space which is complete. So if you have a linear space which has a norm, and if the space with respect to that norm is complete, we call that space a Banach space.